Welcome to this lecture series in coordinate geometry in straight lines. Last time we discussed some basic things about the coordinate plane, the distance formula, etc. Let us recall them. So the coordinate plane is, the basically the Euclidean plane, but we have two perpendicular lines which prescribe two numbers to every point. Uh, the sort of, the first of those two numbers is called the abscissa, the second number is called the ordinate. I'm being a little bit sketchy for the first thing. Then we discussed the notions of the x-axis and the y-axis. Okay, we discussed the distance formula. So if we have 2 points whose coordinates are x1, y1 and x2, y2, then the distance between these 2 points was defined to be the square root of x1 minus x2 square plus y1 minus y2 square. And this was motivated by the Pythagoras theorem. All right, we have the midpoint formula. So suppose we have 2 points x1, y1 and x2, y2. Then the midpoint of these 2 points is given by this formula. Very simple and nice. And a generalization of the midpoint formula was the section formula. So again, we have 2 points x1, y1 and x2, y2 and a point P in between them. And let's say, just as a special case, let's say this was in the ratio 1:2. Then what are the coordinates of P? The coordinates of P are 2 times x1 plus 1 times x2 divided by 2 plus 1, and 2 times y1 plus 1 times y2 divided by 2 plus 1. And you can, in general, if it is 1:2 lambda, then you can see what to write here. Or if it were a is to b, then it would be b times x1 plus a times x2 divided by a plus b, and similarly for this part. So the section formula is a generalization of the midpoint formula. All right. So this lecture will be about centroid of a triangle and an application to trigonometry. And here are some problems for practice. And now let us get started with the basic definitions. I would like to keep this lecture self-contained. So let's define everything. So we have a triangle ABC. And when we say we have a triangle ABC, I mean that the points A, B, C are pairwise distinct, because one could also, in principle, consider degenerate triangles where the 3 points lie on a line or something like that. But all those boundary cases we are not interested in. So we have a triangle ABC. And the median of the triangle ABC passing through the point A is defined as the line passing through A and the midpoint of the opposite side, which is BC. So the median passing through A is the line passing through the midpoint of BC and A. Similarly, the median passing through B is the line passing through B and the midpoint of AC, and similarly for the median passing through C. So that's the definition of the median, very simple concept. All right, here is a fact about quadrilaterals that we will need. We learned this in high school geometry. So we have 2 points B and C, and we have the midpoint of these 2 points. We have some arbitrary line passing through the point M, and again this line L is different from BC. Okay, and now what we do is suppose we draw a line passing through B, whichever line, again different from BC, just some line, and we draw a line passing through C but parallel to this line that we drew. Okay, so this L was arbitrary and this line M is also arbitrary, but this line passing through C is just parallel to M. So this is some construction, and now we get a quadrilateral. So this is some quadrilateral. Let's call this G and call this point H. So then the point is that, what we want to prove is that GC is parallel to BH. We had constructed these two lines as parallel, but it turns out that these two are also parallel. And it's a very simple exercise in congruency. So So let's say this angle is x. Then what is this angle? This angle is also x. Maybe let me magnify everything. Yeah. So let's start again. Suppose this angle is x. Then this angle is also x. Why? Because this line and that line are parallel and these angles are alternate. So these two angles are equal. And of course, these two angles are equal because they are opposite angles. So let's say this is y, then this is y. And now in these two triangles, just apply angle side angle congruency. So angle side angle, angle side angle. So what we deduce is that the side opposite to x, meaning this side, is equal to the side opposite to x, meaning that side. So we deduce that GM is equal to MH. And now, I mean, this is sufficient to finish this because these two triangles are now congruent. Why? Because these two angles are equal. So let me write that also. So this is whatever, let's call that A, and this is A. And now side angle side congruency gives us that this angle, which is opposite to the double dash, is equal to that angle opposite to the double dash. So maybe call it whatever, call it B, and this is B. And therefore, this line must be parallel to that line because these two angles are equal. So, I mean, you can prove everything yourself. Basically, the point is that the figure BCGH is a parallelogram. That's what we want to say. So, therefore, its diagonals bisect as we showed, and the opposite sides are parallel. All right. So, we will use this. So, use this to prove this fact. So, what we have is we have a triangle ABC. We have the median passing through A and the median passing through B. They intersect in a point called G. We want to prove that AG is twice of GM, and this is another way of writing it. So we want to prove this fact, and we will use the midpoint theorem and the fact that we just discussed. So what we will do is we will draw a line passing through C and parallel to this median. So this is that line that we just drew, and let's call this point H. Okay, let me just use white color. This is G, this is H. So now just look at the triangle ACH, this triangle. In this triangle, we have N is the midpoint, and this line is parallel to this line. So by the midpoint theorem, G should also be the midpoint of AH. So we deduce that AG is equal to GH. All right. And here, since this was the median passing through A, we already have these two are equal. So BM is equal to MC is already given to us. And this is some line passing through M. And these two lines are parallel. So by the fact that we just discussed in the previous slide, these two blue lines are also parallel. Okay, these two blue lines are also parallel, and GM is equal to MH. So this is what we just saw. Okay, and to finish the proof, you just observe these two things simultaneously. So AG is equal to GH, but GH is GM plus MH, right? GH is GM plus MH, but GM is equal to MH. So this is twice GM, and hence this is equal to, yeah, that's it. I mean, that's all, because GM is equal to MH, so this is twice GM, and this is what we wanted to show. We wanted to show that AG is twice GM. All right. So once again, first we showed that AG is equal to GH by midpoint theorem, and then by this parallelogram observation, we showed that actually these two things are equal. So AG must be twice of that, because yeah. So we have that fact, and now we, as a result of that theorem, we will deduce that the three medians are concurrent, meaning these three lines pass through a common point. So, sorry. So to prove that, we have these two medians. They pass through some point called G, and then we would like to show that the median passing through C also passes through G. So draw the median passing through C. Sorry. Whoops. Yeah. So let's say it doesn't pass through G or something. So it passes through some point called G prime. But by the same reasoning, AG prime to G prime M is 2:1, and AG is to GM is also 2:1 by the previous slide. So this just forces that G is equal to G prime. Right? There cannot be two different points which separate AM in this ratio. So that's a wonderful fact that the three medians are concurrent, and the point of intersection of the three medians is called the centroid. So the point of intersection of the three medians is called the centroid of the triangle, and we get a fact for free by all this work is that AG is to GM is 2:1, and BG is to GN is 2:1, and CG is to G, let's call this whatever, O is 2:1. So centroid divides the medians in this ratio, 2:1. Okay, and now we are in business to find the coordinates of the centroid. So let's say we have a triangle whose coordinates of the vertices are x1, y1, x2, y2, and x3, y3. We want to express the coordinates of the centroid in terms of these three things. So first, we will write down the coordinates of M. M is the midpoint of this these two points, and hence the coordinates of M are x2 plus x3 by 2, y2 plus y3 by 2. All right, and now we have the point G dividing AM in the ratio 2:1. So by the section formula, the coordinates of the centroid are twice of x2 plus x3 by 2 plus 1 times x1 divided by 2 plus 1, which is 3. And similarly for the y coordinate. So what is the x coordinate? X coordinate turns out to be x1 plus x2 plus x3 by 3, and similarly the y coordinate will turn out to be that. So that's a very nice formula. This is what we get. These are the coordinates of the centroid. Okay, we can remember that. Finally, let us see an application to trigonometry. So we want to say that in any triangle ABC, sine of A plus sine of B plus sine of C is at most this quantity. And you can achieve this when you take the equilateral triangle. So this inequality is tight. Okay, so how do we do this? So suppose, so this is the sine curve. This is 0, and this is pi radians. So let's work in radians. Doesn't matter. This is pi radians, and I hope you're familiar that sine curve looks like this in this range. Okay, and we have the three angles. Let's say this is A, this is B, and this is C. All right. So if we go up and go up here and go up here, so the coordinate of this point is A comma sine A. This point is B comma sine B, and that is C comma sine C. Right? Just think of this as the coordinate plane. Okay, so these are 3 points, some 3 points, and now let's make the triangle. Okay, and somewhere inside will be the centroid. So let's say the centroid is maybe somewhere here. This is the centroid, and we know the coordinates of the centroid are, so the point G is a plus b plus c by 3, comma sine a plus sine b plus sine c by 3. So those are the coordinates of the centroid. So the x coordinate is, so we come here. This is, oops, this is a plus b plus c by 3, which is what? Which is pi by 3 radians, and that's the important point. Because the sum of all the angles of a triangle add up to pi radians. So a plus b plus c is pi, and therefore this is pi by 3. All right, and this length of this line is that much, sine a plus sine b plus sine c by 3. Okay, and finally, since this centroid is inside the triangle, if you go further up somewhere, you will hit the curve. So above the centroid, just keep extending this line. Here, the coordinates of this point are pi by 3, comma sine of pi by 3. Right? So this length is greater than that length, and hence, finally we can write that sine of a plus sine of b plus sine of c by 3, meaning that length, is at most this length, which is sine of pi by 3, and that immediately gives what you want, because sine of pi by 3 is root 3 by 2, and therefore sine a plus sine b plus sine c is at most 3 times root 3 by 2. That's the proof. So a very nice application of the centroid formula and the convexity of, or rather concavity of, the sine curve. In general, this is, there's a general inequality called Jensen's inequality. It's about convex shaped curves, but it's the same thing. Concavity and convexity are brothers. So, that's a nice application. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I'll see you next time.